and welcome to our class once again. In today's class, we'll be talking about sequence divergence. A basic definition for a divergent sequence is that it does not converge. That is, a sequence is said to diverge or is divergent if it does not converge to a real number. If it does not converge to a real number. Now we will recall that when we were working on sequence convergence, we said that if we are given an infinite sequence AN, recall from sequence convergence, that if given an infinite sequence AN, then as n gets bigger, that is, as n tends to infinity, the value of the sequence gets closer and closer to a limiting value a. Closer and closer to a limiting value a. However, not all sequence behaves like this. Not all sequence behave like this. In today's class, we are concerned with sequences that diverges to infinity. Our concern today is on sequences that diverges to infinity. Consider this sequence. Consider sequence xn defined as n over 2. What happens to that sequence as n gets bigger and bigger? Let's consider the terms of the sequence. The terms of the sequence, we have 1 over 2, then we have 2 over 2, we have 3 over 2, we have 4 over 2, we have 5 over 2, 6 over 2, 7 over 2, 8 over 2, and it continues like that to infinity. That shows us that what? As n gets bigger, the value of the sequence diverges or gets larger and larger, which implies that it diverges to positive infinity. It diverges to positive infinity. What does that mean? What does that mean? Now, as n gets bigger and bigger, the value of the sequence gets larger and larger. Now, if we are given a big number, n, given m greater than 0, it implies that what? All the value in the sequence will be greater than n at a certain point. All the values of the sequence will be greater than n at a certain point. Still considering our sequence xn defined on n over 2, suppose m is equal to 100. If m is equal to 100, then at n greater than 200, when our n becomes 200 or even more, the values of the sequence at that point, the values of our sequence n over 2 will be what? Greater than or equal to 100. That now takes us to a more precise definition for sequence divergence. A more precise definition for sequence divergence. Let's look at that definition. A more precise definition for sequence divergence. And what's the definition? It says a sequence AN diverges to positive infinity if and only if, that's IFF, the marker is, if and only if for any m greater than 0, there exists a k belonging to the set of natural numbers such that if n is greater than or equal to k, then an, our sequence an, will be greater than n. On the other hand, a sequence an diverges to negative infinity if and only if for any m less than 0 now, there exists a k belonging to the set of natural numbers such that if n is greater than or equal to k, then the sequence an will be what? Less than n. Now we'll prove this by example. We'll take an example and we'll prove that it is divergent using this definition. Example. Prove that the sequence an defined as minus n over 2 diverges to minus infinity. We want to prove that that sequence diverges to minus infinity. The first thing we need to do is to recall our definition. What does the definition say? It says a sequence a subscript n diverges to minus infinity if and only if for any m less than 0, there exists a k belonging to the set of natural numbers such that if n is greater than or equal to k, then what? Our sequence a subscript n will be less than m. Let's put that down. Again, we have recalled that definition, that a sequence an diverges to negative infinity if and only if for any m less than 0, there exists a k element of the set of natural numbers such that if n is greater than or equal to k, then an or a subscript n will be less than n. Again, the first thing we need to do, we want to identify a k that works. We want to identify a k that works because we want to prove that what? An is less than n. And if that is true, that means that what? Our an is defined as minus n over 2. Minus n over 2 is less than n. And this implies that what? Our minus n is less than 2n. If minus n is less than 2n, then what? N will be greater than minus 2n. N is greater than minus 2n. And that implies also that our k is greater than minus 2n. We can now prove it. Let epsilon be greater than 0 and let k, element of natural numbers such that k is greater than minus 2n for all n greater than or equal to k. We now want to show that truly our an is less than n. We want to show that truly our an is less than n. To show that an is less than n, we start from our an, and our an is what? Our an is defined as minus n over 2. But n is greater than or equal to k. But n is greater than or equal to k. And we have said that k is greater than minus 2n. That implies what? That minus 2n is less than our k. And so sequence an, which is equal to minus n over 2, is less than minus into minus 2n over 2. This is less than 2m over 2, and our sequence an is less than n. Therefore, it implies that the limit as n tends to infinity of the sequence an is equal to minus infinity. That is, the sequence an defined as minus n over 2 diverges to what? Minus infinity. And that is what we have proven there. We'll take one more example and see that it also diverges. We'll take another example and we'll prove that it also diverges. You can pause the video to try your hands on this. See if you are able to prove it. We'll take another example now and prove that it is actually divergent. Prove that n squared, the sequence n squared, diverges to positive infinity. It means that we want to show that the limit as n tends to infinity of n squared equals positive infinity. You will recall the definition of sequence divergence. Now remember, this is diverging to positive infinity. It says a sequence an diverges to positive infinity if and only if for any n greater than 0, there exists a k belonging to the set of natural numbers. There exists a k belonging to the set of natural numbers such that if n is greater than or equal to k, then our sequence an will be greater than n. Then our sequence an will be greater than n. Again, the first procedure is identifying a k that works. We want to identify a k that works. In order to identify a k that works, we will begin from an greater than n. And what's our an in this case? That's the sequence n to the power 2. N squared is greater than n. And if n squared is greater than n, it means that what? It implies that n is greater than the square root of n. And if n is greater than the square root of n, recall that we have assumed our n to be greater than or equal to k. Therefore, k is also greater than the square root of n. Therefore, to prove, we need to make certain assumptions. Let m be greater than 0 and k be greater than the square root of n for all n greater than k. If that is the case, remember that our sequence an is equal to n squared. And if sequence an is equal to n squared, we have assumed that n is greater than k. And if n is greater than k, therefore n squared will also be greater than what? K squared. And if n squared is greater than k squared, remember our k is greater than square root of m squared. Therefore, this is also greater than what? The square root of m all squared. So our n squared is greater than the square root of m squared is n, because the square square of the square root. And so that implies that our sequence an is greater than n. Therefore, the sequence n squared diverges to plus infinity. positive infinity. If you have benefited anything from today's class or this video, give it a thumbs up, like it, and share with your colleagues. Thank you. God bless you. I see you in the next video.